Welcome to the fastest way to learn data structures and algorithms. Today, we're mastering a classic graph and matrix challenge, LeetCode 130, surrounded regions. This problem is a perfect test of your DFS and BFS intuition. Mastering this border inward strategy is a game changer for your technical interview prep. The goal is to capture all regions that are completely surrounded by X. We do this by flipping O's into X's. But there's a critical rule: any O that is on the border, or connected to an O on the border, cannot be captured. These cells are safe. Our job is to find the trapped O's and flip them, while leaving the safe ones alone. Think of this like an island rescue operation. The O cells are islands, and the X cells are the enemy ocean. Islands that touch the edge of the world, the board border, have a path to the mainland and are safe. Any island trapped in the center, completely walled off by the enemy ocean, is captured. To solve this, we start our rescue team at the borders, and follow every connected path inward to mark all the safe islands. We use a three-step border inward approach. Step 1, we patrol the 4 borders of the board. If we find an O, it's safe. Step 2, from every border O, we run a depth-first search to mark all connected O cells with a temporary marker, like T4 trapped no more. Step 3, we scan the entire board. Any O that wasn't marked is surrounded, so we flip it to X. Finally, we change our T markers back to O. Simple, efficient, and zero redundant work. Look at the board. We have a 4x4 grid. We start our border patrol. On the top row, we find an O at column 3. This is our starting point for the rescue. We trigger DFS. From this border O, we check its neighbors. Below it, at row 1, column 3, is another O. We mark both as T. They are safe. Now we patrol the bottom border. We find an O at row 3, column 1. Another DFS starts. It has no O neighbors, so we just mark it as T and move on. The patrol is finished. Now for the capture phase. We scan the whole board. Look at row 1, column 1. It's an O, and it wasn't marked as T. It's trapped. We flip it to X. Finally, we turn all T's back into O's. The mission is complete. In our Python code, we first define our DFS helper. It checks if a cell is within bounds and is an O. If so, it marks it as T and recurses to all 4 neighbors. Next, we loop through the board's borders. For every border cell, we call our DFS. This seeds the rescue operation. After the border DFS is done, we use nested loops to iterate through every cell in the grid. If a cell is still O, it must be surrounded, so we set board at C to X. If it's T, we restore it to O. For time complexity, we visit each cell a constant number of times during the border patrol, DFS, and the final scan. This gives us O of m times n, where m and n are the board dimensions. For space complexity, the recursion stack for DFS could, in the worst case, go as deep as the total number of cells, so that's also O of m times n. And that's how you rescue surrounded regions like a pro. If this breakdown made the logic click for you, hit that like button and subscribe to Leo Academy for more premium DSA guides. See you in the next one.